The next type of load that we're going to investigate is a random vibration input. So random vibration studies are actually a statistically based analysis, and it's using linear dynamics. It's actually a frequency-based solution. And our inputs to this type of analysis are going to be magnitude versus frequency. So 1 G load up to about 250 hertz or so. In automotive, the frequencies are quite a bit lower. And this is random vibrations. So if we extract our test data, it looks a little something like this. And the input then becomes a frequency versus amplitude. So I can reuse all my connectors and fixtures from my other studies. And the way I would begin is I would just start my new study and go down to linear dynamic and choose the type of linear dynamic study. We could do a modal time history, which would be similar to our impulse, but it would be linear material properties, sinusoidal or harmonic waveforms, random vibration, and then response spectrum analysis, which is very often used for military specs. You can kind of think of the random vibration, the response spectrum, and the harmonic studies as something that you would use, that you might do on a shaker table. So let's go to our flight cruising loads. Our connections, our fixtures are essentially identical, and the only thing that we have to change is our base excitation as a waveform. Okay, so now, as I mentioned, random vibration analysis is a statistical-based solution. So we're going to look at what's called a PSD stress response. And then we'll notice when we probe the stress value, so we're going to go back to our fillet at the same hot spot that we're seeing. I'll pick a spot on my fillet. And then when I say give me the time history response, I'm actually going to get a frequency-based response. So what this is telling me is I have a resonance in my system around 38 hertz, and that's where all the magnitude of my stress response is coming from. Because this is a frequency-based solution, I can go and look at my frequency plots and see which shape is this. So I say list my resonant frequencies, and my second mode of vibration for the structure is around 40 hertz or so. And that's right around the 38 hertz that's causing all the damage in our part. So let's look at the second mode shape, and a little bit intuitively, we have a cantilevered mechanism here, and this is the mode shape that's causing all the problems. So it tells us what we need to do essentially to attack these high stresses. We either need to have something that kind of hold our gear in place when it's stowed, or we need to stiffen up our mechanism to shift this mode shape to a higher frequency. Obviously, the more structurally efficient method might be to have some sort of linkage that kind of holds our gear in place when it's stowed, but that's going to be more links and more actuators.